Welcome to the comprehensive guide on autonomous vehicles interview questions. Today, we'll explore the core concepts that form the backbone of self-driving technology. Autonomous vehicles represent one of the most exciting frontiers in modern technology, combining computer vision for visual perception, sensor fusion for comprehensive environmental awareness, machine learning for intelligent decision-making, and path planning for safe navigation. These four pillars work together to create vehicles capable of operating without human intervention. Understanding these concepts is crucial for anyone seeking to work in this rapidly evolving field. The Society of Automotive Engineers has defined 6 levels of driving automation, from level 0 to level 5. Level 0 represents no automation, where the human driver performs all driving tasks. Level 1 is driver assistance, where the system can assist with either steering or speed control, but not both simultaneously. Level 2 is partial automation, where the system can control both steering and acceleration, but the human must remain engaged. Level 3 is conditional automation, where the system can drive independently, but requires human intervention when requested. Level 4 is high automation, where the system handles all driving tasks within specific operational design domains. Level 5 represents full automation, where the vehicle can operate autonomously under all conditions without any human intervention required. Computer vision is the foundation of autonomous vehicle perception systems. Convolutional neural networks form the backbone of modern object detection systems, enabling vehicles to identify and classify objects in real time. YOLO, which stands for You Only Look Once, is a popular object detection algorithm that can process images quickly enough for real-time applications. Image segmentation helps vehicles understand the precise boundaries of objects and road surfaces. Feature extraction allows the system to identify important characteristics of detected objects. Real-time processing is critical because autonomous vehicles must make split-second decisions. The basic computer vision pipeline starts by loading a pre-trained neural network model, processing the input image through blob conversion, and then running forward inference to detect objects in the scene. Sensor fusion combines data from multiple sensors to create a comprehensive understanding of the vehicle's environment. Primary sensors include cameras for RGB and infrared vision, LiDAR for three-dimensional point cloud mapping, radar for distance and velocity detection, and EMU GPS systems for position and orientation tracking. The fusion pipeline begins with data collection from all sensors simultaneously. Preprocessing involves calibrating and filtering the raw sensor data to ensure accuracy and consistency. The fusion algorithm, often using Kalman filters, integrates all sensor inputs to create a unified environmental model. This multi-modal approach provides redundancy and improves reliability, as different sensors excel under different conditions. For example, cameras work well in good lighting, while radar performs better in adverse weather conditions. Machine learning enables autonomous vehicles to make intelligent decisions based on complex environmental data. Deep learning uses neural networks with multiple layers to recognize complex patterns in sensor data. Reinforcement learning allows vehicles to learn optimal driving policies through trial and error, receiving rewards for safe and efficient behavior. Decision trees provide rule-based decision-making for handling specific traffic scenarios with clear logical paths. Ensemble methods combine multiple machine learning models to create more robust and accurate predictions. The neural network example shows a basic autonomous model architecture using TensorFlow. It includes convolutional layers for processing image data, dense layers for feature processing, and an output layer that produces control commands. This type of architecture can learn to map sensor inputs directly to driving actions through supervised learning on large datasets. Path planning is responsible for determining safe and efficient routes for autonomous vehicles. The A-star algorithm provides optimal pathfinding using heuristic search methods to find the shortest path while considering obstacles. Rapidly exploring random trees, or RRT, efficiently explore high-dimensional spaces to find feasible paths in complex environments. Dijkstra's algorithm calculates shortest paths in weighted graphs, useful for route optimization. Dynamic programming enables optimal control for smooth trajectory planning. The planning pipeline starts with map generation and localization to understand the vehicle's position. Obstacle detection and avoidance identify static and dynamic obstacles in the path. Route optimization and smoothing create efficient, comfortable trajectories. Finally, motion control execution translates the planned path into actual vehicle movements through steering, acceleration, and braking commands. Technical interviews for autonomous vehicle positions focus on core algorithmic concepts and their practical applications. Candidates should be able to explain how sensor fusion works and why it's critical for safe operation, including how different sensors complement each other and handle various environmental conditions. Understanding the differences between YOLO and RCNN for real-time object detection is essential, particularly their trade-offs between speed and accuracy. Path planning questions often involve implementing dynamic obstacle avoidance in complex urban environments with moving pedestrians and vehicles. Kalman filters play a crucial role in autonomous vehicle localization systems by combining GPS, EMU, and visual odometry data to maintain accurate position estimates even when individual sensors experience temporary failures or degraded performance. System design interviews evaluate candidates' ability to architect complete autonomous vehicle systems. Key questions include designing the overall system architecture for a Level 4 autonomous vehicle, which requires understanding how perception, planning, and control layers interact. Ensuring low-latency processing for critical safety decisions involves optimizing algorithms, using specialized hardware, and implementing efficient data pipelines. Implementing redundancy and failover mechanisms for sensor failures requires designing backup systems and graceful degradation strategies. The typical system architecture consists of three main layers. The perception layer handles sensor fusion and object detection. The planning layer manages path planning and decision-making, and the control layer executes vehicle actuation. Each layer must be designed for reliability, real-time performance, and safety. Safety and ethics questions explore critical decision-making scenarios that autonomous vehicles may encounter. Handling sensor degradation in adverse weather conditions like heavy rain or fog requires robust algorithms and backup systems. Fail-safe mechanisms must activate when the primary AI system encounters unknown scenarios, potentially transferring control to a human driver or executing emergency maneuvers. Implementing redundancy for critical safety systems involves multiple independent systems that can take over if one fails. Ethical scenarios include the famous trolley problem, where vehicles must decide between different harmful outcomes. The passenger versus pedestrian dilemma questions whether vehicles should prioritize occupant safety over external road users. Data privacy concerns involve balancing the need for vehicle learning and improvement with protecting user location and behavioral data from unauthorized access or misuse. Success in autonomous vehicle interviews requires mastering several key areas. Technical depth means understanding core algorithms and their trade-offs in real-world scenarios, not just theoretical knowledge. System integration involves knowing how different components work together in the complete autonomous vehicle stack, from sensors to actuators. Real-time constraints require understanding latency requirements and optimization techniques for safety-critical systems where milliseconds matter. Safety considerations must always be paramount, with ethical implications considered in every solution. For interview success, practice explaining complex concepts simply and clearly. Stay current with the latest research and industry trends as this field evolves rapidly. Prepare thoroughly for system design scenarios that test architectural thinking. Finally, understand regulatory frameworks and safety standards that govern autonomous vehicle development and deployment in different regions around the world.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.